Welcome to the fourth Introduction to Real Analysis lecture. The topics that we will explore in this lecture include partitions, partially ordered sets or posets, and functions. Okay, so let's start with the exercises from the previous lecture. And the first we will state as a theorem. So let A and B be sets. Then A is a subset of B if and only if the union of A with B is the superset B, and A is a subset of B if and only if the intersection of A and B is the subset A. So proof, first statement, assume that A is a subset of B. Now, since it is always true, that a set, in this case B, is a subset of any union which contains it, it remains to show that the union of A and B is a subset of B. So let X be an element in the union of A and B. Then either X is in the set A or X is in the set B. So suppose that X is in the set A, then since A is a subset of B, X is an element in the set B. So now suppose that X is in the set B, then that element remains in the set B. So in either case, if X is in the union of A and B, then this implies that X is in the set B, and hence the union of A and B is a subset of the set B, and thus the two sets are equal. The union of A and B is equal to B whenever A is a subset of B. So conversely, assume that the union of A and B is the set B, and let X be an element in the set A. Then X is an element of any union which contains A. So in particular, it is in the union of A and B, which is the set B. That is, if X is in the set A, then X is in the set B, and hence A is a subset of B whenever the union of A and B is equal to B. And therefore, A is a subset of B if and only if the union of A and B is the superset B. So second statement, again assume that A is a subset of B. Now, since it is always true that an intersection, in this case the intersection of A and B, is a subset of any of the individual sets in the intersection, in this case the set A. It remains to show that A is a subset of the intersection of A and B. So let X be an element in the set A. Then, since A is a subset of B, X is in the set B. That is, X is in the set A and X is in the set B. And so X is in the intersection of A and B. And thus we have that if X is in the set A, then this implies that X is in the intersection of A and B. And hence the set A is a subset of the intersection of A and B. And so we have set inclusion in both directions. And so the intersection of A and with B is the set A whenever A is a subset of B. So conversely, assume that the intersection of A and B is the set A. Let X be an element in the set A. Then X is in the intersection of A and B. And that intersection is always a subset of any of the individual sets in the intersection. And so it is a subset of set B. And so X is in the set B. That is, if X is in the set A, then this implies that X is in the set B. And hence, A is a subset of B whenever the intersection of A and B is the subset A. And therefore, A is a subset of B if and only if the intersection of A with B is the subset A. So next, we'll look at an example, which we left as an exercise from the previous lecture. So let P be the set of all polynomials in the indeterminate X with integer coefficients and let tilde be a relation on that set of all polynomials defined by X is related to Y. Oops, we're doing polynomials. The polynomial F is related to the polynomial G if and only if the derivative of F is equal to the derivative of G Recall from basic calculus that the derivative of two functions are equal if they differ only by a constant. So now we want to show that this relation is an equivalence relation. So since it is true that the derivative of a function f is equal to itself, by the definition of the relation tilde, f is related to itself. So it is the relation is reflexive. So suppose that f is related to g, then the derivative of f is equal to the derivative of g. And so the derivative of g is equal to the derivative of f. And hence g is related to f. And so the relation is symmetric. So now suppose that f is related to g and g is related to h. Then f prime is equal to g prime and g prime is equal to h prime. And so f prime is equal to h prime. And thus f is related to h, and so the relation is transitive. And therefore, since the relation tilde is reflexive, symmetric, and transitive, it is an equivalence relation. On the set P. So new definition. If for every element I in a non-empty set, which we'll call capital I, there corresponds a set A sub I, then the set which we denote script A of all sets A sub I for I in an element in the set capital I is an indexed family of sets with the set I, the indexing set or index set. So let's use this concept to define a new type of intersection and union. So let the collection script A of sets A sub I for I in some set I be an indexed family of sets. The union of all the sets in the collection script A is the set which we denote union for all elements I in the set I of the sets A sub I. And this is the set of all the elements X such that X is in the set A sub I for at least one index I in the set I. We sometimes call this an arbitrary union. And the intersection of all the sets in the collection script A is the set, which we denote this way. The intersection for I in the indexing set I of the elements, or the sets A sub I, is the set of all the elements X, such that X is in the set A sub I for every index I. And we sometimes call this an arbitrary intersection. So often, the index set is a subset of the set of positive integers which is denoted Z superscript plus. So if the indexing set I is the entire set of positive integers, we can write the arbitrary union this way. The union from I equals 1 to infinity of the sets A sub I, and we can write the intersection of all the sets A sub I this way. It's the intersection from I equals 1 to infinity of the sets A sub I. Now sometimes we do not have an indexing set, but we can still speak of the union of all the sets in a collection of sets. So let script B be a collection of non-empty sets, collection of non-empty sets. Then the union of the elements B in that collection is a set of all the elements X, such that X is in a set B for some set B that is in the collection, script B, and the intersection of all of the sets B in the collection, script B, is a set of all the elements X, such that X is in the set B for every element B in the collection, script B. Okay, so new definition. A partition of a set S is a collection which we denote as script P of non-empty subsets of the set S such that every element of S is in exactly one set in the collection script P. That is, the collection script P is a partition of the set S if and only if the empty set is not in the collection script P, the union of all of the sets P in the collection script P is the entire set S, and if I is not equal to J, then the set P sub I intersected with the set P sub J is the empty set. That is, a partition is a collection of non-empty subsets of a given set where the union of all those sets in the partition is the entire set, and no two sets in the partition have any elements in common. They are pairwise disjoint.